August 6, 1945, 8:15 a.m., Hiroshima, Japan. A small object falls from the sky, slicing through the morning air. It detonates 600 meters above the ground. In an instant, the city is bathed in a light brighter than the sun. A fireball erupts, searing everything within a kilometer. A shockwave follows, leveling buildings like they were made of paper. Tens of thousands die instantly. This is the power of the atomic bomb. But how does such a small device unleash the energy of 1,000 suns? How does physics transform a tiny amount of matter into an explosion that can wipe out entire cities? Today, we will uncover the science, the mechanics, and the horrifying aftermath of nuclear detonations. To understand an atomic explosion, we must first delve into the very fabric of matter, into the heart of the atom itself. Every atom consists of a nucleus at its core, made up of protons and neutrons, surrounded by electrons in orbit. The nucleus is held together by an immensely powerful force called the strong nuclear force, one of the four fundamental forces of nature. In most elements, the nucleus is stable, but in certain heavy elements, like uranium-235 and plutonium-239, the nucleus is unstable. This makes them susceptible to a phenomenon called fission, the process that powers atomic bombs. Nuclear fission occurs when a neutron strikes the nucleus of a heavy atom, splitting it into two smaller nuclei and releasing an enormous amount of energy. This process also releases additional neutrons, which then collide with other atoms, creating a chain reaction. The energy released comes from the conversion of mass into energy, following Einstein's equation, E equals mc squared. Where E is energy, m is the tiny amount of mass lost during fission, and c is the speed of light, roughly 300,000 kilometers per second, squared. Because c squared is such a huge number, even a minuscule amount of mass is converted into an unimaginably large amount of energy. For an atomic bomb to detonate, the chain reaction must be rapid and uncontrolled. This requires reaching a state called critical mass, the minimum amount of fissile material needed to sustain a chain reaction. If too little fissile material is present, the reaction fizzles out. But once the critical mass threshold is reached, the reaction becomes self-sustaining, triggering an explosion in a fraction of a second. Now that we understand the physics, let's break down the mechanics of an atomic bomb, how it's built and how it detonates. Every fission bomb consists of one fissile material, either uranium-235 or plutonium-239, 2 neutron initiator, a device that releases neutrons to start the chain reaction, 3 explosive lenses, high explosive charges that compress the fissile core, 4 tamper and reflector, a shell that reflects escaping neutrons back into the core, increasing efficiency. There are 2 primary methods used to detonate an atomic bomb gun type design, which was used in Hiroshima's Little Boy. In this method, 2 subcritical masses of uranium-235 are separated inside the bomb. A conventional explosive fires one piece into the other, achieving critical mass and triggering a chain reaction. This design is simple but inefficient, requiring large amounts of uranium. Implosion-type design, used in Nagasaki's Fat Man. This method is far more sophisticated. A spherical core of plutonium-239 is surrounded by high explosives. When detonated, these explosives create a perfectly symmetrical shockwave, compressing the plutonium into a supercritical state. A burst of neutrons then triggers the chain reaction. This design is more efficient and allows for much smaller bombs. Within microseconds, the atomic bomb's core reaches millions of degrees Celsius, hotter than the sun's core. The surrounding air is instantly turned into plasma. A fireball begins to expand outward at supersonic speeds. The fireball grows to hundreds of meters in diameter. Everything inside it vaporizes: buildings, steel, concrete, human beings. The light from this fireball is so intense that it instantly blinds anyone within several kilometers who looks at it. The explosion creates an intense pressure wave moving at hundreds of meters per second. At ground zero, the pressure is equivalent to tons of TNT per square meter, enough to reduce everything to dust. 1 kilometer away, concrete buildings are shattered. 5 kilometers away, windows are blown out and people are thrown through the air. A blast of thermal radiation ignites everything in its path. Within 1 kilometer, skin and clothing ignite instantly. Up to 5 kilometers away, people suffer third-degree burns. 10 kilometers away, exposed skin is severely burned. In Hiroshima, shadows of people were burned into walls, forever marking the moment of their vaporization. That's just the first 3 sections of this 10,000-word document. The next parts will cover radiation and fallout, how deadly radiation affects survivors, the long-term aftermath, the horrors of radiation sickness, environmental destruction and genetic mutations, modern nuclear weapons, how today's bombs are thousands of times stronger than Hiroshima's. I'll continue with the next sections, keeping the tone dramatic yet scientifically detailed. As the fireball expands and the shockwave tears through the city, another deadly force is unleashed: ionizing radiation. This radiation comes in 3 primary forms: gamma rays, the most penetrating and lethal. They travel at the speed of light, passing through buildings, skin, and even bone, damaging DNA at the molecular level. Neutron radiation, high-energy neutrons that cause secondary radiation as they collide with other atoms, making materials radioactive. Beta and alpha radiation, less penetrating but still deadly if inhaled or ingested. Within milliseconds of detonation, anyone near ground zero is exposed to a lethal dose of radiation. Cells are destroyed, internal organs suffer irreversible damage, and the body begins to shut down. Survivors who are not immediately killed by the blast face an even worse fate: radiation poisoning. Minutes after the explosion, dark, oily rain begins to fall, black rain, a mixture of radioactive debris, soot, and water vapor condensed from the firestorm. Anyone caught in this rain unknowingly absorbs lethal radiation through the skin. The particles settle on the ground, homes, and bodies of survivors, continuing to emit radiation for days, weeks, and even years. The fallout is carried by wind currents, contaminating areas hundreds of kilometers away, 5 kilometers from ground zero. Fallout covers everything, increasing cancer risks. 50 kilometers away, radiation levels are still dangerously high. 500 kilometers away, traces of radiation are detected in soil, water, and food. In nuclear tests conducted by the United States and the Soviet Union during the Cold War, fallout was detected halfway around the world, a reminder that no one is truly safe from nuclear war. Radiation doesn't just kill, it lingers in the body, rewriting genetic codes and destroying tissues from the inside out. There are 2 main types of radiation sickness. 1, acute radiation syndrome, or ARS, occurs within hours or days after exposure to high radiation doses. Symptoms include nausea, vomiting, and diarrhea, severe burns and blisters, internal bleeding, immune system failure leading to infection, and death within weeks if the dose is high enough. 2. Chronic radiation exposure. Survivors who receive lower doses experience increased risk of leukemia and other cancers, genetic mutations leading to birth defects, organ damage, and premature aging. Survivors of Hiroshima and Nagasaki experienced higher rates of cancer for decades. Many children born to exposed parents suffered severe birth defects. The effects of radiation poisoning are not just personal. They pass down through generations. The atomic explosion doesn't just destroy buildings, it ignites entire cities. The intense heat sets everything flammable on fire: wooden houses, paper, fuel, even asphalt. The rising heat creates a firestorm, sucking in oxygen and turning the city into an inferno. At ground zero, temperatures exceed 4,000 degrees Celsius, hot enough to melt steel and turn sand into glass. Firestorms spread outward, consuming survivors who weren't killed in the initial blast. Oxygen is burned away, suffocating those trying to escape. In Hiroshima, the firestorm burned for hours, leaving only skeletal remains of buildings behind. The physical destruction is only half the story. The survivors, the hibakusha, faced immense suffering. Many were rejected by society due to fears of radiation sickness. Psychological trauma led to decades of depression and PTSD. The city became a ghost town where life seemed impossible, yet against all odds, survivors rebuilt. But the scars, both physical and emotional, never faded. The atomic bombs of Hiroshima and Nagasaki were small compared to modern nuclear weapons. Unlike atomic bombs that rely on fission, hydrogen bombs use nuclear fusion, the same process that powers the sun. A fission bomb acts as a trigger, creating the extreme heat needed to fuse hydrogen isotopes, deuterium and tritium. This fusion reaction releases 1,000 times more energy than fission. The result? A single hydrogen bomb can annihilate an entire country. The largest bomb ever detonated, the Tsar bomber, had a yield of 50 megatons, more than 3,300 times the power of the Hiroshima bomb. Today, there are over 12,000 nuclear warheads in the world. If a full-scale nuclear war broke out, the consequences would be apocalyptic. Hundreds of millions dead within minutes. Nuclear winter, smoke and ash would block sunlight, causing global crop failures. The collapse of civilization, radiation, disease and starvation would wipe out survivors. The world has come close to nuclear war multiple times, from the Cuban Missile Crisis to Cold War standoffs. Despite international treaties, nuclear weapons still exist in massive numbers. The risk of accidental launches, terrorist attacks, or geopolitical conflicts remains. The only way to prevent nuclear annihilation is through diplomacy, disarmament, and global cooperation. The atomic bomb is the most terrifying weapon ever created. It serves as a reminder of human ingenuity, but also of our capacity for destruction. The question is, will we learn from history, or are we doomed to repeat it? The story of the atomic bomb is one of science, destruction, and survival. Understanding its mechanics and consequences is not just about history. It's about ensuring that such a weapon is never used again. The future is in our hands.